All right. So for the last talk, and this is not deja vu, it really is Arslan one more time. Yes, and we expect to see what the difference between these two are because the titles look the same. So
just remember that question.
Remember what was the question?
That how do we do the safety stuff in kernel?
Yes, I'm very excited about this because we've implemented this stuff in LLVM and Linux, and it is a pain in the butt. All right.
I know.
I'm excited.
And this is the work that's similar to nested kernel, so you're gonna like it.
All right. Excellent. All right. So take it away, Arslan.
All right, thank you. The next work I'm going to present is called EC, Embedded System Compartmentalization via Intra-Kernel Isolation. Some familiar words there. So CRTC, there's a recent work that was published in Oakland 23. They used privilege separation.
Yeah! There you go!
But when they presented their work, someone pointed out that the kernel compartment is kind of big. So what do we do about that? So it's a big compartment. We need more compartments in it. We need some compartments. And also, it might have a lot of unsafe code. They just said that it's a kernel compartment, so you just just trust it. It doesn't sit right with us, so we have to solve this. So at this point, we'll go beyond the type safety land, and we'll see how we can secure type unsafe code that's written in C that's low level. All right, so again, the motivation is that we want subcompartments in the kernel compartment. So our review from the previous talk. We have compartmentalization, we have a program dependency, 2 phases, identification, and enforcement. So right now, we are in the same area. We want to have low overhead. But this time, we're not going to play with type safety. But we still want some compartmentalization in the kernel. So how do we do identification? Because in the last work we used privilege, it doesn't really work here because it's the same privilege level. So technically, there are several ways to partition it. So our approach here is that we say that it depends on your workload, what kind of partitioning you want. We just give you full kind of control that you want for compartmentalization. So to this end, we provide another compiler called ECC, which has some cool extensions that can guide the identification process. This compiler has some extensions that converts to LLVM IR, and we have an LLVM pass that converts it to a PDG with annotations about RTOS resource usage. We export this annotated PDG to a Python plugin, and this Python plugin can partition the PDG based on any specification. It could partition the PDG based on threads. It can partition the PDG based on file usage. It can partition the PDG based on different components of the system. So for an example, let's take the component policy, because traditionally we are more familiar with different components in the kernel, right? So if you talk about different kernels, components in the kernel, our annotations will tell you which part of the PDG belongs to which component. And based on your Python plugin, you can put all of the nodes from one component into one compartment. And that's how we identify different compartments in the system. But we still have not talked about how can we do isolation among these compartments. And I did not lie. I'm not going to use type safety again. So, but first of all, naive enforcement, the bad technique that we can implement. So as you remember, everything is running in the same preview mode. So if you want to isolate different compartments from each other, what you can do is technically you can move everything in the unprivileged mode, have a security monitor in the privileged mode, and whenever you have cross-compartment interaction, you call the security monitor. The security monitor uses memory protection hardware. And it changes the view of the compartment, goes back. But people did not even use context switching in the normal embedded system work. So we're back to high overhead land. So, and this is not going to sit right with the existing people. And one more thing that we need to notice here is that whenever you're moving the whole firmware from the privileged mode to the user space or the unprivileged mode, there's going to be some non-trivial porting effort. So our solution here is intra-kernel isolation. So the runtime that we provide is called the EC-kernel. EC-kernel basically sits beside the firmware in the privileged world, and it basically mediates the access to the memory protection hardware, which is called the MPU in the embedded system. If you're not familiar with the MPU, MPU is just like an MMU, but just crappier. It does not do memory translation. It has very limited protection regions that you can protect, and that's pretty much it. So in order to mediate access to the MPU, ECK uses watch points. So it uses the debug extensions in ARM controllers. If you want to access the memory protection unit and you try to access it directly, it will trigger a watch point, which will be routed to the ECK because of the debug exceptions are routed to ECK. And ECK will just deny access to any MPU accesses. So how does memory switching works in this system? So the legal way to switch the compartment is that you talk to ECK. ECK basically masks the debug exception and freely access the MPU. Now you might ask, why can't the normal firmware mask the exceptions? And the reason is there are special instructions for masking exceptions. And now, because there are special instructions for masking exceptions, we can do a static analysis, or we can do a binary analysis to filter out all of the instructions and make sure that the normal firmware is free of these instructions. Lastly, our ECK is a very, very, very small piece of code. It's less than 500 lines of code. And to make sure that it's safe, we do formal verification to ensure it's memory safe, thread safe. And we also ensure that whenever we get a context switching request, we switch to the correct compartment. Because of this unique design, EC is almost 1.2, actually not almost, it is 1.2 times faster than the state-of-the-art solutions. To evaluate EC, we conducted our evaluation on different softwares. We conducted our evaluation on FreeRTOS, STM32F4F which is a bare metal application project, and STM32F7Q, which is also a bare metal application project. And because there's so much diversity for these softwares, we conducted our experiments on 3 different microcontrollers: STM32F4, STM32F46, STM32F76. All right, so as far as our evaluation for security is concerned, the security benefits that you're going to get depends on the application, and it also depends on the policy. So for example, we have implemented a couple of policies. Thread policy, where we put every thread in a different compartment. Component policy, which is we put every component in a different compartment. File policy, every file in the, or each compilation unit, separate compartment. Device, all of the compartment is guided from like different device drivers. And color is basically like a greedy algorithm, which basically just like partitions the PDG based on a greedy approach. As you can see, if you have a finer grain policy, you have more ROP gadget reduction. But if you have a finer grained isolation, you have higher overhead. Again, here you can see different applications, different policies. And based on the policy, you might get as high as 60% overhead, or if you play your cards right, you might get really low overhead. So in some cases, you only get like 0.2 something percent overhead. Oh, memory overhead. So memory overhead is kind of tricky with the memory protection unit. Overall, you can see that EC results in about 2.4 times memory overhead. And the reason is because of MPU. MPU cannot protect arbitrary regions in the memory. So it has specific alignment requirements. And if you want to protect a region, you have to place it in a specific place in the memory. And because of that, you might have some fragmentation in the memory. And because of this fragmentation, we see most of this overhead. As far as like the ECK code and ECK data is concerned, as I mentioned earlier, the microkernel itself is very, very tiny. So we only incur around like 3% overhead for the code and the data. And most of the overhead is coming from the alignment requirements and the fragmentation that we had to do to make sure that we can protect all of these compartments. Maybe in future, if MPU design improves, we can get rid of this overhead. All right, conclusion. So we provided a new compiler that has language semantics that can guide the identification process for compartmentalization frameworks. We have introduced a new fast isolation mechanism based on intra-kernel isolation. And we evaluated this work on real-world platforms and real-world software. I would like to mention this as well, that although these two works are both doing compartmentalization, hopefully everyone can see that the targets for compartmentalization are kind of different. And these work are kind of complementing each other, not targeting, like going at each other. All right, so with that, I would like to take any questions you guys have. Hi.
Kelly Kiotis from Trail of Bits. Since you're mentioning that these works are complementary, do they have the same threat model, or are you considering different attackers for each work?
So we are considering different threat models because if you remember, like someone asked, right? Because in that work we just said that kernel is trusted, but in this work we are like, okay, like even not the kernel is trusted. So we have different threat models.
Awesome, thank you so much.
Thank you.
Hi.
Hi.
I'm Ian Cabras from UCSC. I'm not sure if this applies exactly to your setting, but you said you use static analysis to make sure MPUs not accessed directly. How about JIT? Can you protect against that too?
Oh, that's a good question. In embedded systems, we don't see a lot of JIT.
It's just not there?
Yeah, so the workload that we have in embedded system is like statically linked, like all of the thing is like is running in the same program. I don't think I've ever seen any work doing like JIT or like a dynamic program for embedded system. But yeah, that would be interesting. Like if a use case arises, we'll probably have to like take about that as well.
Thank you.
Yeah.
Hey, Tribhar from EPFL. So I had a question. I'm not very familiar with the STM microprocessors which you use, but I'm assuming they have this memory protection unit or something. So what happens when you go to even lower power devices where you don't even have any MMU and you have some sort of operating system, firmware, and application all running together in the same privileged domain? Is there any way to protect against this use case?
So for that use case, I think the best you can do is CRTC, the previous work. Because even if you, and there are controllers that don't even have MPU.
Yeah, I know, it's quite popular.
Yeah.
Cortex-A series.
Yeah. No, Cortex-A has MMUs. So there are Cortex-M0s, which are really, really low powered. So, I kind of should have mentioned, so we need the debug extensions here as well, right? So we do target embedded systems, but for the really low power embedded systems, I guess you're just stuck with CRTC. I mean, I will still give you a solution.
Thank you. Well, let's talk offline.
All right, sure.
All right, let's go ahead and thank our speaker and the whole session.